Well, my talk today is about this project that's funded by Tran-SET and by New Mexico DOT as well. And this project is on retrofitting corroded metal culverts using glass fiber reinforced polymer composites. Before I start, I'd like to acknowledge my co-authors and co-workers, my PhD student, Raul Reda and my colleague, Dr. Susan Bogus-Holter, who is the director of Tran-SET Center at UNM.
Sorry,
it doesn't work?
It doesn't click, it just points.
Okay, that's okay. So background quickly about why we are doing this. What is the motivation of the project? Is nationwide, and actually many places also worldwide, metal culverts is being used under highways, an important structure for floods and flood control and for protecting the highways. Many of those structures in the United States have been built in the 1950s and the 1960s. So they are exact example or a great example for the work Tran-SET is looking at, which is how can we maintain this infrastructure, and because many of those culverts nationwide are corroding. In New Mexico, that's a case. In many other states, in Texas, in Louisiana, as I heard, in many other states, this is a problem, and many people are seeing this is a problem. The design life is about 50 years. Corrosion dropped this to be below 30 years. TRB looked at the problem and saw a substantial increase in failures of these metal culverts with time. Examples we have seen nationwide. Highways suddenly collapse. You can see here a collapse because of corrosion of the culvert, and you can see a highway suddenly collapsing and resulting in a catastrophic collapse, preventing the use of the highway or the road here. So the corrosion, with the current rate of corrosion of those metal culverts, is inevitable, and the cost is not the cost about the repair or putting a new one. It's a cost about closure of those major highways. In New Mexico, we have this case happening under I-40. I-40 is a major highway connecting many states and going through Albuquerque. So if you have a case like this happening on a major highway, that is a closure that is going to cost a few $1 million if you close that highway for a day or two. So our interest, our idea was actually to slide a glass fiber reinforced pipe, polymer pipe. And I say pipe, but it does not have to be a pipe. It can be any cross section, because those GFRB sections, or what we call as profiles, can be made to any section using filament winding. And they need to be designed to match the existing culvert cross section. So we are working with the DOT on actually taking the exact shape of these existing culverts using some 3D imaging technique, and actually generating these profiles using the glass fiber polymer sections, and then grout the metal, the gap between them, with a polymer concrete or grout material. So the design will include the design of the GFRB profiler section and the design of the polymer concrete to actually do the load transfer. Objectives or values for using glass fiber reinforced GFRP materials or composites: it's high strength, lightweight material, stronger than steel, and it's lightweight. It's corrosion free. So, and if we design it to make sure that actually it is capable of providing the same hydraulic job, then there is no change in the use of the culvert. It can also serve in severe environments. So if you replace with any other material that would corrode, will be a problem. Here you can use it in severe corrosion environments like in Louisiana. The very nice thing, actually, can be produced in a variety of shapes. We are not limited to existing pipes. We can take the shape and we can manufacture it, and then we can, and the exact dimensions that would slide in this cross section. So that was our proposal to Tran-SET that got funded and got the interest of New Mexico DOT. And what we were asked by New Mexico DOT is early when we had the idea, they were worried about the fact that the glass fiber, the GFRP composite section, will not have a good composite action with the steel, and there could be failures in the bond. So we were asked to actually look at the retrofit methodology, all of it, how we were going to slide the material, what polymer we are going to use, test the strength in culvert, and make sure there is a composite action. And then develop a computational model to aid in the design. So what we did is the first thing is we went with worked with New Mexico DOT and identified a number. This is a plan from one of the New Mexico DOT guides about the culverts with the different dimensions. We decided to take an 18-inch culvert, and many of them, by the way, is not circular. Many of them are elliptical shapes and other shapes. But we took a circular one that is existing, and we know that is its height, and it's 18-inch, and we decided to replicate a case like this. And all of these, this could be, we are showing here for metal. This could also be done for concrete culverts. Could be done for other types of culverts with the same technology. But here we are presenting the case for metal culverts. So once we identified the design, we went and got a new pipe that is the same exact dimensions that is used in the culvert in New Mexico. That's an 18-inch. We use 90-inch length of the pipe just because of the limitations we have in testing. Otherwise, we can't do the full-scale testing. We worked with a company in Arizona to actually do the filament winding for us, on that would fit exactly that dimension and that profile, and that's a 16-inch GFRB with a thickness of 0.35 as per our design to take the load on this. To start the work, we need to do some surface grinding of the profile of the pipe or the GFRB section. Again, if this is being produced for that project, that step might not be necessary. But this is again just a glass fiber profile produced for any other use as well. So we have to roughen the surface to make sure that is good bond. Another important thing is we have to work with the producer to identify what type of resin is used with the GFRB, and that's what we did, because there are a few resins usually used with GFRB. Could be epoxy, could be vinyl ester or polyester. In this case, we asked them to use an epoxy because it's got to be the same resin and epoxy material to be used with the grout to maximize the bond between the polymer concrete or grout and the GFRB pipe. So here we are showing that after all the grinding and things, we are cleaning and washing with a water jet the outer surface to be ready for application. The next here is we are showing an example of the sliding. So this is just the pipe and the lab, and all you need to have is to have some spacers to be able to slide the pipe in the steel pipe. Of course, in the field it will be a little different, but we are just showing here it's absolutely simple, nothing difficult. The next step for doing our test, our simulation, is we actually went at the end and post the sliding, and we put a thick epoxy layer at the end so that it will allow us, which can be another and wood section at the end, which you would need to do at the exact culvert so that you limit the place where you are going to have the grout. On the pipe itself, again, that will be in the part of the design of the real project. We have a hose connected to the pipe here and here, so that that will be also need to be designed in the field when this is field applied, so that you can pump the polymer concrete on one side and get it on the other side, so that you make sure you fill all the gap. So this is the producing the polymer concrete. We have an epoxy resin. We've done about 10 trial mixtures until we reach the trial mixture with the polymer concrete that have the required shear strength, the good bond with the GFRB, and also good flowability to allow it to flow in the gap, because we have a very thin gap. We have about less than 1 inch, because this is, talk about inner diameters, but we have corrugations in the steel pipe. So we mix the materials, add filler, 3-5 minute mixing, and then basically it's a amine-based epoxy similar to the GFRB, and then we have this hand pump which can be easily used to pump the material. And again, trial mixes were required to make sure that will work. I'm going to show here a quick video on the grouting method. So this is the research team who actually does the work. And you can see here the polymer concrete going on the other side from the other part of the pipe after filling all the gap. So after this, we started planning to do the experimental testing and for the full-scale pipe. So this is the steel pipe, as you can see, with the GFRB inside it, with the polymer concrete between them. We waited on it for a week before we do the testing. And we instrumented, this is a 400 kib actuator. We did special bearing plates on both the sides, the top and the loading plates, and here to allow the sliding on this side and to allow having the same shape with the corrugation here to be a pin and here to be a free side. We used the different LVDTs and strain gauges to make sure that we are measuring the composite action. So just this schematic shows that this is the LVDTs, these are strain gauges. So we put strain gauges on the glass fiber, and we put strain gauges on the outer side as well, inside and outside side of the glass fiber, strain gauges on the steel. Our objective is to be able to have a profile, make sure that the flexural profile is achieved, and to make sure that the glass fiber is carrying the load as we are doing the testing. We use LVDTs to get the displacement. We also use LVDTs at the end to make sure if there is any horizontal longitudinal shear movement, if there is a slip, that's going to happen. So this is a summarized video. The testing took 5 hours to actually do the full testing. So that's just an edited video. And we stopped the testing because of the excessive deformation. We did not stop the testing because of failure, but because we reached the deformation level that after this we are going to be start hitting the machine. But there was no abrupt failure. So this is the results. I'm showing here first the load deflection. I'm going to talk more about it. And you can see here the strain profiles in the material. So it's the glass fiber, as you know, is linear elastic material, and the different load profiles here with a significant ductility of the composite section to about 3.5 inch. That's where we stopped the loading. And you can see that we have the total capacity of 74 kib. The New Mexico DOT was talking about that if we can reach between 30-35 kib, that will be great because that's the capacity of the soil. And actually, we passed this. So this shows you here the different points where steel yielding with separation of the corrugation happened. And this is the failure of, actually you start seeing failure in the glass fiber. And this is the one at 0.8 deflection. So this shows the different profiles and what happens. Now this quickly here, to see this is very interesting because you can see that at 76 kib, the glass fiber failed inside. So you can see failure, which means that the glass fiber is taking all the load, the composite action is working perfect, and actually the glass fiber is the reason why this section is now carrying 76 kib. This is filament winding at 45 degrees, so the failure was exactly as we expected. This is again the deformed shape, and this is the finite element model we developed to simulate the behavior. And our objective of using the finite element model is we actually will be using to design the GFRB. So we use it with Abacus because that would allow us to actually design the glass fiber with the different layers. We can put the layers and the direction of the filament winding for design. So in conclusion, we believe we have done a reasonable and comprehensive retrofit technique that shows that we can actually increase the expected life to 75 years with using GFRB pipe or profile to be slid inside the corroded metals. Composite action is confirmed. The composite section exerted maximum yield capacity actually of 75 with significant high ductility that you wouldn't see with others. The polymer concrete did not fail, and there was no debonding in this, which is great. Future work we are looking at, we are repeating the test in our lab now with corroded pipe. So we corroded one pipe completely, and we are repeating that exact test with the corroded pipe. We're adding some materials in the polymer concrete to ensure bond with the corroded steel. We're using nanomaterials to actually improve both the grout and the GFRB if needed. We will validate the finite element, as I said, to use it for design. And we are talking with New Mexico DOT on field implementation. So they are interested now to actually field implement this with sensors on the field. Would like to acknowledge Tran-SET and the companies that worked with us and New Mexico DOT. I'd like to acknowledge the research team who did the work. I only here comes always to take credit, but they are the ones who did this work, and I would be happy to answer any questions.